Yeah, so what is the issue? Oh. No, if it falls, it's good, right? The lecture will end. What a relief. Okay. So let us start the third lecture, and that will be about. So I will just start from here. Quasi-normal modes of black holes, and we'll try to derive these quasi-normal modes analytically and using some techniques that you are already familiar with, for example the WKB method. Okay, that is what we'll do it. There are many ways of obtaining QNM, like continued fraction method, shooting method, and so on and so forth, but most of them are mostly numerical. I mean, you do not get an analytical result out of them, but using the WKB approximation, which you are pretty well used to in quantum mechanics, but still I will try to go over it slowly just to make all of you comfortable with it. And using that, we'll derive the QNMs, and as promised, I will try to show how these QNMs are related to the photon sphere, which we have studied in the last lecture. So that will be the main part of this talk. Now, before I go to the QNM, I mean, normal mode is something that is very familiar, I guess, to most of you. So, if you have a string and you perturb it slightly, it vibrates with its characteristic frequencies. And this is true for any system. Like, you must have done small oscillations in your classical mechanics course. And one of the main aim of this small oscillation course was to find out the characteristic frequencies of an object when you perturb it slightly. So, for example, if you have a gyroscope or whatever object you have, there would be principal axis and there would be principal frequencies of vibrations around them, and this forms one of the main part of the small oscillations, I think. So, similarly, when you perturb a black hole is also going to oscillate just because it's also some object. But the only point is, instead of calling it normal mode, we are calling it as quasi-normal modes, because the frequencies are complex. I will try to explain why the frequencies have to be complex and what are the equations and how do you solve them and so on and so. Because mostly all of physics corresponds to solving second order differential equation. So black hole is no exception. Here also we'll get a second order differential equation which we'll try to solve, as simple as that. Okay. Now there can be three types of actually there are more perturbation, but normally three types of perturbation. One is you have scalar perturbation, which is due to a scalar field. Please do not confuse it with cosmological perturbation, where scalar vector and tensor carries different meaning than what you do in gravitational sector. Here scalar perturbation means you are solving box phi equal to the Klein-Gordon equation in some background metric g mu nu. Then there is electromagnetic perturbation, which is solving Maxwell's equation in a part of background. The assumption why these are perturbation is because you do not assume that scalar field is back reacting on your geometry. You are simply assuming that there is a metric which is not perturbed by the scalar field. So the calculations will all be at the linear order. As you can easily anticipate, that T mu nu would depend on quadratic of the scalar field, like del mu phi, and so on and so forth, and those are quadratic in the potential or quadratic in the scalar field, which we are ignoring. So this is the linear perturbation theory, and I guess you have get a flavor of this earlier from Adam's talk, but we'll do whatever we require for our purpose. Then electromagnetic we have discussed. The final is the gravitational perturbation, whose equation Adam has already discussed with you, where you take g mu nu going to g mu nu plus h mu nu, and you determine the field equation for h mu nu. If it is flat background, then you simply have box h mu nu equal to 0. If there is curvature, then first order you have box h mu nu plus Riemann times h mu nu equal to 0, and you solve them. But here the idea would be your background is not flat, of course, because background has a black hole, and gravitational perturbation would be difficult to do on blackboard here because it requires too many other amenities. So therefore we will restrict to scalar perturbation, but the point is the end equation that we will obtain would be very similar to what you get in the context of gravity. So you will get a feel for it as well. So as I said, our aim is to study the Schwarzschild metric. So I will take it to be 1 minus 2m by r dt square. So I am rewriting it just for the sake of it so that it remains here. Okay, so this is my Schwarzschild metric and my scalar field satisfies this equation, which is box phi equal to 0. This must be very familiar to all of you, the Klein-Gordon equation, which is the first step that you learn when you do your classical field theory courses. I can rewrite it as 1 by minus g del mu of g mu nu, g mu nu del mu of phi equal to 0, right? This is the equation. So the box, if you expand, you will get this. The reason this root minus g comes about, I guess you all know. When you compute grad mu of a mu, you can write in terms of gamma, and gamma with 2 index contracted gives you derivative of log root minus g. So that is the origin of this root minus g factors over there. Now the next job is to use this metric g, plug it in here and try to simplify this equation. Okay, I will do a few steps just so that you can follow it properly, and then we'll jump back to the final answer. So the root minus g for this metric, as you can easily anticipate, is pretty simple. It is r square sine theta, because when you do root minus g, these two terms are going to be multiplied with each other, giving you 1. Then from here you get r square from g theta theta and r square sine square theta from g phi phi, multiplying. You are taking square root, which gives you r square sine theta. And so if you plug that back in, then what you get is the following. So you have 1 by r square sine theta, then you have del t of r square sine theta. GTT is minus 1 minus 2m by r. Let's put it inside bracket. Then you have del t of phi. Now you can see that neither r square nor sine theta nor 1 minus 2m by r depends on the t component. So therefore I can pull all of them outside. So r square sine theta cancels with the r square sine theta term over there, and I am only left with this term, which is minus 1 by 1 minus 2m by r times del t square of phi. Right. So that means the first term, of course there would be additional terms which I will come back to, the radial part and the theta part, but at least the first term I can simplify and write it as del t square of phi divided by 1 minus 2m by r. Now comes the next term, where you take your mu to be r, nu to be r, and g upper rr component, which gives you 1 by r square sine theta del r of r square sine theta 1 minus 2m by r in times del r of phi. Right, again it makes sense. This is root minus g, this is root minus g, this is g upper rr, and you have del r and del r over there. Again the sine theta can be cancelled, because you know it's a derivative with respect to r, so theta smoothly goes outside. So I can just remove this sine theta and rewrite this as del r of r square 1 minus 2m over r del r of phi. So the r part is done. Then I have the theta part. So theta part would be r square sine theta del theta of r square sine theta del theta of phi by r square. So this is root minus g, this is root minus g, and 1 by r square comes from the g upper theta theta component. Again r square I can take outside, because del theta of r is 0. So I will have rewritten this as 1 by r square 1 by sine theta del theta of sine theta del phi del theta. Correct? This comes from the theta. The final thing that remains is the phi derivative. Now as you know, the metric also does not depend on phi, so I can take everything outside. So I mean, rather I am just writing the final thing. So let us make it capital phi, just to make sure that our notations are not messed up. Yes. Okay. What is the issue? Okay, you can put it here itself. Thanks. Okay, so is this fine? Any doubt? Yeah, you can ask me. Yeah, that's all. So you get this particular result. Now, as you know, what is the next thing to do is to, if you can use separation of variables as a trick, so then you know that the t and phi and they are going to decouple. So the normal trick is to write phi as e to the minus I omega t e to the I m phi r of r times theta of theta. The standard, I mean, when you have done electrostatics and you are solving, you know, solving the Poisson's equation in a cubic box, you would separate between x, y and z, or when you are solving hydrogen atom in quantum mechanics, you would solve your Schrodinger equation into r of r, theta of theta into phi of phi. Phi of phi will have this e to the I m phi. The only additional piece is this e to the minus I omega t. Right? I mean, if you are, you know, too much into rigor, then what you should do, you should write it as t of t, you should write it as phi of phi, and then separate things and solve. But I mean, there is no need for doing that because we know that things are separate. Now, if you plug them in back over there, then you will get omega square by 1 minus 2m by r plus 1 by r square del r of, actually I can rewrite in much better way, 1 by r square ddr of r square 1 minus 2m by r into d capital R over dr, and plus I will have 1 by r square, I think I will have a capital R over here because I am dividing, 1 by r square, and I will have 1 by theta, 1 by sine theta dd theta of sine theta into d theta, and plus I will have minus rather m square by sine square theta equal to 0. Right, this is pretty easy. I mean, derivative of this, which is here, minus del t square of phi, will give you omega square. It is total derivative because capital R only depends on R, and the rest of it just follows. This minus m square comes from double derivative of capital phi with respect to small phi. This I square gives this minus sign. Now, the quantity inside the bracket, you must all know what is the differential equation for this. This is the PLM cos theta, the associated Legendre polynomials, right? And the separation constant which comes out of it is L into L plus 1, correct? And that is something that we all know. So, therefore, my theta simply becomes PLM cos theta, and as you know, e to the I m phi multiplied with PLM cos theta gives me the spherical harmonics which are YLM theta phi with some extra factor like 4 pi by 12 plus 1 and so on and so. So that means this whole part goes away and I will have minus L into L plus 1 by r square equal to 0. So as promised, this is a second order differential equation and everything only depends on r. So you have the omega dependent part which is present over there, and you have the L dependent part which is present over there, and then there is a term which depends on double derivative of r. Now at this stage what you do is that you introduce this interesting, yes, of course. No, I have a 1 by r there, so there is no multiplication by r. So I have a division by capital R. So when you multiply, it will automatically be multiplied with r. Okay. So this is called the tortoise coordinate. Okay, I hope you are all familiar with it, but still let me define it. For Schwarzschild, it is a piece of cake. So the tortoise coordinate r star is defined as integral dr over 1 minus 2m over r. Okay. And this integral you can easily perform. I will not do it, but the result is something like this: r plus 2m log of r minus 2m over 2m. So you can see the usefulness is when r is very large, then r star is same as r, right? Because when r is large, r is much larger than log r, of course. For example, if I take r to be 10 to the power or e to the power 10, for example, this will just give you 10 because of the log, while this will give you e to the 10, which is much larger than 10. On the other hand, when r is closer to the horizon, which is r equal to 2m, then it's the log term which starts to dominate, because log of 0 goes towards divergent values, and actually when r goes to 2m, your r star goes to minus infinity. That means you do not have to worry about the finite region 2m to infinity. You can work with this tortoise coordinate which spans from minus infinity to plus infinity. That actually helps you in many ways, as I will show. So then people, what they do, they changes this variable small r to r star, and it is pretty easy to do. As you can see that you can use this condition that 1 minus 2m over r times ddr is nothing but ddr star. Okay, it simply follows from here that dr star is dr divided by 1 minus 2m by r. So dr star is dr with 1 minus 2m by r on the top. So that means this object over here, I can simply replace it with dr by dr star. Correct? But then, I mean, you want to rewrite it further. So what you have to do, you have to do some additional manipulation. So what you have to do, you have to define a psi, which I think is capital small r times capital R. And after you have done this rescaling, so that power I am not 100% sure, you should put it can be 1 by r as well, but that you can check for yourself. But the idea is you want to write the differential equation in the form of a Schrodinger equation. So what is Schrodinger equation? d2x by dx square, or d2 psi by dx square, plus e minus v into psi equal to 0. Right, or with a minus h bar square by 2m and so on and so forth. So that means I do not want any term which is linear in the derivative. So that is ensured by this particular rescaling which is present, because if you normally do it, you would get a term which is linear in r, like d capital R by dr star, which I do not want to have. So that can be done by this simple rescaling, which you can check afterwards. And after you do all that, you get back your equation, which is d2 psi by dr star square plus omega square minus vr star psi equal to 0, and this v of r star will turn out to be 1 minus 2m by r L into L plus 1 by r square plus 2m over r cube. So you see, this is the form which is after. You have second derivative term d2 psi by dr star square, then you have plus omega square minus, which is easy to see. This is the term which gives rise to d2 psi by dr star square. You already have a plus omega square which is present over there. Then L into L plus 1 by r square is there. There is a multiplicative factor of 1 minus 2m by r, which comes from this term, which is omega square by 1 minus 2m by r, and this extra piece which is present, which is effectively the derivative of 1 minus 2m by r, that comes from the fact that I have used this rescaling, and when you expand this derivative, there would be a constant piece which will come from there. You can play the same game with electromagnetism as well as with gravity. Okay, so for electromagnetism, you get exactly the same equation, just that. So let me put it as V0 just to ensure that this is scalar. Then you have the same equation for electromagnetism with a different potential, omega square minus V1 of r star psi equal to 0, but this V1 would be the same 1 minus 2m by r, but it would simply be L into L plus 1 by R square. Now for gravity, the problem is, I think this maybe Adam has already discussed. So to discuss gravitational perturbation, you generally decompose it into axial part and polar part. So gravitational perturbation is described by a symmetric matrix which is in 4 dimension, which means it will have 10 independent components. Correct? Any metric will have 10 independent components. Among that 10, 3 will transform as odd under parity and 7 will transform as even under parity. So there would be 3 components of this metric perturbation which is odd and 7 components of the metric perturbation which are even. Now in addition, you have gauge transformation. As you know, if you change that your x mu going to x mu plus xi mu, which is also called diffeomorphism, then you can actually change your metric elements. So diffeomorphism gives you 4 degrees of freedom because xi mu is a vector which has 4 components. You can show that among those 4 components, 1 is axial and 3 are polar. So that means you had 3 degrees of freedom in the axial sector. One of them can be eliminated by gauge choice. In the polar sector, you had 7 degrees of freedom. 3 among them can be eliminated by gauge choice. So this is the diagram sort of that you should remember. You had 10 degrees of freedom in your H mu nu. Among them, 3 are axial and 7 are polar. Then you have the diffeomorphism vector xi mu, which has 4 independent components, and among that 4 you use one component to reduce this to 2 degrees of freedom in the axial sector. Here you use 3 components to reduce it to 4 degrees of freedom in the polar sector. So that is how it goes. And what are these 2 components? These 2 components corresponds to, so if you write down the axial, it will be something like 0, 0, H0, H1. This is G theta phi. This will also be H0 and H1. This will also be H0. This will be H1, 0, H1. So this is the form of the metric perturbation in the axial sector. You have perturbations in the GT theta component. You have perturbations in the GT phi component. You also have perturbations in the GR theta component and GR phi component. These are same. And then by symmetry, this should come over there, that should come over there, and so on and so forth. Now, okay, I think I have made a small mistake. This should be H1. This should also be H0. Yeah. But anyway, the point is there are 2 independent degrees of freedom to fix. One is H0 and one is H1. That means you would expect that there would be 2 equations, one equation for H0 and one equation for H1 coming out of the axial sector of the metric perturbation, which means you are perturbing Einstein's field equation by using this particular choice for H alpha beta, and that should give you the necessary answer. Now what turns out to be a miracle is that given these 2 equations, you can actually combine them to get a single differential equation, which is called the master equation or the Rayleigh-Wheeler equation, because Rayleigh and Wheeler first derived this equation in old days like 1957 or so, I think. But I mean, just to make you yourself caution that if you read the original paper by Rayleigh and Wheeler, there are several errors in that paper. And you should actually read, if you want to learn these things, is a paper by Visheshwara in 1972 or 73 with Edelstein. In that paper, all the equations are written correctly. So if you quote these results from the original paper of Rayleigh-Wheeler, there is a finite chance that you are getting the equations wrong because there are errors in those papers. So if you want to learn it, Edelstein Visheshwara's paper is the one to go for. So after you have done all of this manipulation, the equation that you get at the end for the axial sector is exactly the same, with the potential being modified by, I will write it as VRW just to argue that it is Rayleigh-Wheeler or to remind you of the Rayleigh-Wheeler. It simply is L into L plus 1 by R square minus 6m over R. So this is scalar, this is electromagnetic, this is axial gravitational perturbation. The polar gravitational perturbation on the other hand has this form where you have a H0, you have H1, H1, H2, these are all 0, then you have K. So you count the number H0, H2, H1, K, 4 degrees of freedom, which is exactly the 4 degrees of freedom that you have in the polar sector. Now among them you can show by calculation, I will come back to this in detail, that H0 is same as H2. So that means effectively you have 3 unknown constants, 3 unknowns to look for. Here also you can do your miracle, and this was done by Zerilli again, like more than 10 to 12 years later, like I think 1972-73, where he found an exactly similar equation. Even for the polar sector you can define a similar master equation, but the potential is a bit more complicated than this, which I am not going to present. But the point is, even for the Zerilli potential, this term is present, which is the most important one. The rest of it has some a little bit more complicated behavior. So all in all, to summarize whatever we have done, take any perturbation, scalar perturbation, electromagnetic perturbation, gravitational perturbation. Gravitational perturbation, axial sector, polar sector, whatever you do, always you can write down your metric in this form, which is like a Schrodinger equation, but the potential is different in different cases. With one similarity, all of them has 1 minus 2m by r outside, all of them, and they all have this term which is L into L plus 1 over R square. Right? Clear? Now let me remind you of something. So do you remember in the last class we worked out what is the effective potential that a massless particle experiences? So the potential was exactly this, if you remember, with L into L plus 1 replaced by the square of the angular momentum. Yes.
So this is the thing that you summarized just now. So this is only true for Schwarzschild because we're only focused
Correct.
on Schwarzschild.
Correct.
So if we
Sure.
like if we stick to current and all those things, then it will be
Rotating black hole is what you mean. Okay. The problem with rotating black hole is that you cannot get an equation of this form, because for rotating black hole, if you want to do metric perturbation like what we do here, then the equation becomes unmanageable because of the complicated nature of the background. So what you do in the study of rotating black hole is to use something called the Newman-Penrose formalism, which was developed by Tucholsky and others around of the same time, 72, 73, 74. And that gives you a different equation which is not of this form, and you try to solve those Tucholsky equation in order to get the relevant QNM. Okay, so those equations are more complex and hence I will not go into them, but will stick at least as of now to the simpler equations. Any other questions? Yeah, of course, because the Kerr metric has this very special structure that the geodesics are separable. So even if you write down box phi, you can separate it out. The only problem there is, there would be this Carter constant and other things coming in. So the equation would be a bit difficult, but for scalar, see what I am saying to your question is for gravitational perturbation. Scalar perturbation or Kerr can be studied in exactly the similar way. There is no difference over there, but the equations would be different. Any other question? Yes. Yes. Oh, that's psi. So that's psi. Again, I'm quoting from memory. If I'm not wrong, it was something like this. DDR of H1 by R. Okay, so you take H1, then there is some combination, you take its derivative, whether this is 1 by R or R, I don't remember exactly, and that gives you the Regge-Wheeler psi. So this psi over here, like for Regge-Wheeler, you will have a psi that is related to H1. And you know that H1 is related to H0 by one of the Einstein's equation. So you get two equations. One equation using which you can replace H0 in terms of H1. Then you can use that in the other equation to get a single differential equation for H1, in which you can make this substitution and get it to this particular form. Yeah, for electromagnetic case, there is one catch which I did not mention. The point is, as I mentioned, electromagnetic is a 4 vector. So that means it will have one part which is axial, one part which is polar. It turns out both of them give rise to the same equation. So this psi here, I mean, for the axial case, this is related to the, what should I say, the theta, some combination of theta phi component, and some r kind of scaling is there. For the axial, for the polar, there would be some linear combination that you have to take. Okay. Any other question? Okay, wonderful. Yes. Regge-Wheeler is axial and polar is Zerili. Pardon me? Zerili, Z-D-R-I-L-L-I. Okay. So this is Regge-Wheeler, that is Zerili. Fine, everyone? Now let me go to the next step, which is finding out the QNMs and why they are complex. So the point is to solve this differential equation that we have over here. And what can you solve it for? So in the case of Schrodinger equation, what do you do? Given some potential, what are your aim? Can you tell me? Correct. Solve for eigenvalues and eigenfunctions, right? Here what I am going to do, I have given you what is the potential for each of these cases. Just like this is like particle in a box, this is hydrogen atom, this is harmonic oscillator, various potentials for various cases. So you have to solve an eigenvalue problem with whose eigenvalue? This omega. So I have to find out what are the eigenvalues of omega, correct? And also what are the eigenfunctions psi effectively. So I will not compute the eigenfunctions, I am just concentrating on eigenvalue. So the job is to determine what is omega, just like in quantum mechanics. Now the next question is, whenever you do things in quantum mechanics, you need boundary conditions, right? You cannot solve it arbitrarily. When you solve particle in a box, you put boundary condition that my wave function should vanish at r equal to 0 and r equal to a and so on and so forth. Similarly, here also you need boundary conditions. So that is the most important part in the QNM analysis. So to understand the boundary condition, let me draw the potential. So I will draw the potential in units of in r star coordinate. So as you know that r star goes from minus infinity to infinity, which I had already discussed with you. And second thing that you know is what is the nature of this potential. Okay. Now if you go to r equal to 2m, then can you tell me what happens to these potentials? They all vanish because of this 1 minus 2m by r in the front. What happens when r goes to infinity? Then also it goes to 0. So this potential is 0 here, which is r star minus infinity, which corresponds to r equal to 2m. This potential is also 0 over there. Good. Now what I am going to say, you can verify by yourself. If you take derivative of each of these potential and second derivative, you can show that they all have only one maxima. None of them have a minima in the problem. So that means this potential will generically look like this. So that there is maxima at some radius, which is here. It goes to 0 as you approach infinity. It goes to 0 as you approach minus infinity. So this is the generic potential, nature of the potential for any of these cases. Whether you take scalar, whether you take electromagnetism, whether you take gravity. By gravity, I will just restrict myself to Regge-Wheeler. Fine. Now you may ask why that is so. So the calculation that I am going to do is what is known as the eikonal approximation. You may have heard about it in your geometrical optics course. And this means assuming that L is much greater than 1. Now if you assume L to be much greater than 1, what happens between these potentials? You can ignore this 2m over r cube term because L is much larger. You can ignore this 6m over r cube term because L is much larger than 1. That means all of this potential reduces to this one alone. And this potential you already know. What is this potential? This is the potential of a massless particle experiences in Schwarzschild background. So that means this maxima is located where? At the photon sphere. So that means if you are looking at modes which are much greater than 1, with L much greater than 1, they experience the same potential that a photon experiences in a Schwarzschild background, with a maxima which is located at r equal to 3. So you realize that we are doing a very different problem. Earlier we were just doing motion of a particle in a given Schwarzschild background. Now we are studying that perturbation of that background under various perturbation like scalar, electromagnetism and gravitational perturbation. And if you are interested in the limit where L is much greater than 1, then all of them actually boils down to motion of a massless particle in a curved background. You can understand why easily, because scalar we have solved box phi equal to 0. So this is massless scalar. We have solved electromagnetism, Maxwell's equation, photons are massless. We have done gravitational perturbations, and gravitons, so to speak, are also massless. So these are all massless particles whose potential I am drawing, and when L is much greater than 1, then that effectively means you are going to a geometrical optics limit in which the particle just moves through without any wave or any other nature. So that is equivalent to motion of a massless particle in Schwarzschild background, and hence you get back the same potential. There is no surprise, so to speak, but this is an interesting fact to keep in mind. Yeah, exactly. Spin in the sense, for scalar you say spin is 0, electromagnetic is spin 1, gravitational is spin 2, so they are not relevant. They all satisfy the same equation, same potential. Pardon me? Yeah, this is R star. Okay, I will put that is r equal to 3m, and r is thought of as a function of r star. Okay, you can convert it, but yeah, it would be something like 3m plus 2m log of 1/3 or whatnot, half probably. Up to this point, do you have any question or comment? So if not, then I will go to our WKB approximation. Okay. So what is done in WKB approximation? Do you remember? All right. Okay. So in WKB, what you do is that you solve an equation which is of this form. So think of Schrödinger's equation, h bar square over 2m d2 psi dx square plus E minus V, which I am collectively calling as Q times psi equal to 0. Now h bar is a small number, so that means I will take the limit where epsilon is much smaller than 1. Right? Then I will rewrite my psi as exponential 1 by epsilon summation over n equal to 0. Then you have psi, how do I put it, psi n epsilon. You must have come across this series before, because when someone asks you that, well, you have Schrödinger equation, can you get back Newton's law from it? What do? You say, I will take h bar tending to 0 limit, but if you take h bar tending to 0 limit of Schrödinger equation, then it's a disaster. You get E square is equal to V, which makes no sense at all. So therefore, what you do rather is you use this type of an expansion, which is exponential I divided by h bar, and then there is a summation which is an expansion in h bar. You need a 1 by h bar term. And that is exactly the reason when you write down phases in quantum mechanics, it is not exponential I h bar, it is something times h bar, like time translation operator e to the power I e t or h t by h bar. Then if you write down space translation operator e to the power I p x by h bar. So it is exactly the same which is being done here. So for our purpose, we will just work with the simplest choice, which would be exponential of 1 by epsilon psi 0 plus psi 1 into epsilon, such that this is sorry, correct? Makes sense, everyone? Then you plug this back over here. So you just have to take two derivatives of it. So you get epsilon square. Let me do it step by step. So d psi dx, if I do, I will get psi, then I will have psi 0 prime by epsilon plus psi 1 prime. So if I take double derivative, I will have psi into psi 0 double prime by epsilon plus psi 1 double prime plus psi into psi 0 prime by epsilon plus psi 1 prime square, and then I will have q into psi. How do I write it here? So let me write it here. It is epsilon square psi into psi 0 double prime plus epsilon plus psi 1 double prime. Then I have psi into psi 0 prime by epsilon plus psi 1 prime square, and finally I have q into psi equal to 0. Correct? So this just comes from double taking another derivative of this one. So first you take derivative of psi, so you can again use this relation. Second, you keep psi fixed and take derivative of the rest. Then if you expand, you see psi cancels out from all the sides because there is a psi here, there is a psi here, there is a psi there. So you will get this equation as epsilon into psi 0 double prime plus epsilon square psi 1 prime to psi 1 double prime. Then you are squaring it, so you will have psi 0 prime square and plus twice psi 0 prime psi 1 prime epsilon plus again there is epsilon square psi 1 prime square plus q equal to 0. So I am just multiplying. So first term is psi 0 double prime into epsilon because it is multiplied with epsilon square. Next term is of order epsilon square. The last term, when you are squaring, the first one is 1 by epsilon square, so there is no epsilon. Second term, you are multiplying these two, so there is a 1 by epsilon, there is epsilon square outside, which gives you linear in epsilon. Last term, psi 1 prime square, it gets multiplied with epsilon square, and that gives you epsilon square. Right? Fine? Clear? Okay. So I will ignore all the terms of order epsilon square because there also I am not keeping it, and then I will equate the terms which are independent of epsilon to 0, the terms which are linear in epsilon to 0. Actually this you can go as a series, you can relate terms up to order epsilon squared to 0, epsilon cubed to 0. The more order of terms you keep, you are going to higher and higher orders in your approximation. But you have to keep in mind in this series also you should keep to higher and higher orders. Here I have kept terms up to linear order in epsilon, so it only makes sense that I keep terms here also up to linear order in epsilon. If you want to keep terms up to quadratic in epsilon, you should add another term to this series which is of order epsilon square. So both of them should be consistent. Then you get two equations. One is psi 0 prime square plus q equal to 0 and psi 0 double prime plus 2 psi 0 prime psi 1 prime equal to 0. So this is the 0th order equation, this is the first order equation. Correct? Fine. Now this equation is your Newton's law in quantum mechanics. Can you see that? So this is what is known as the Hamilton-Jacobi equation. So you never get the Newton's equation, so to speak, from Schrodinger equation, but what you get is the Hamilton-Jacobi equation, because this Q contains your energy and the potential, and this psi 0 prime is nothing but your momenta. So this means p square plus potential is equal to energy, which is nothing but your Newton's equation or the Hamilton-Jacobi equation. And the second equation is where you have quantum corrections to the system, which starts from order psi 1. So classically you just get this equation in quantum mechanics. If you have not done this exercise, you should do that because it is important. Right? So the Newtonian limit or classical limit of Schrodinger equation is Hamilton-Jacobi equation, which is the first one. Now I have to solve these equations, which are pretty easy to solve. So the first equation, what is solution for psi 0? As you can really understand, it would be integral up to x with maybe plus or minus square root of minus q dx prime. See, psi 0 prime is square root of minus of q, correct? And then I am integrating. And from the second equation, you see that psi 1 prime is equal to minus half ddx psi naught prime. What you do, you take the psi naught prime to the other side. So it is derivative of psi naught prime by psi naught prime, which gives me log of psi naught prime, and the half comes through. So that solves for psi 1, which is minus half log psi naught prime. Psi naught prime is already square root of minus q. So this becomes minus half log square root of minus q, and that brings it to log of q to the minus 1/4. Okay. Should I explain it again? See, I am solving this equation, first one, which is very easy. It's a single. For the second one, you take psi naught prime below. So that is a log of psi naught prime. So that's what I have done, log of psi naught prime. And this equation I can easily integrate to get psi 1 to be minus half log of psi naught prime. Psi naught prime I know, which is square root of minus q, then there is a minus half. So a log x is log of x to the power a. So you take minus half as power of this, which gives you minus q to the minus 1/4. So then if you substitute it back into this equation, which is psi 0 and psi 1, you know what is your psi 0, you know what is your psi 1, you obtain that your psi with minus q to the minus 1/4 exponential plus minus, let us not put I, integral up to x root minus qx prime dx prime. This is the result that you will have. Fine? Clear? Okay, now you will say, why have I done all of this? Because now is where our physics starts. So far it was all mathematics. So I want to find out my omegas, means I have to find out my eigenvalues. As I said, to determine my eigenvalues, I need boundary conditions. Okay. So for Q and M, the boundary conditions are as follows. I will just write them down here. So the boundary conditions are psi should be purely outgoing as r star goes to infinity, and psi should be purely ingoing at horizon. The boundary condition at horizon should be pretty apparent, because at horizon nothing can comes out, everything has to fall into the horizon. So the perturbations also should be purely ingoing at the horizon, and it should be purely outgoing at infinity, right? And this is something which tells you why the normal mode frequencies of black holes must be complex. Why? If you do normal quantum mechanical system, classical system, the main thing that you use is the conservation of energy. That means the total energy that you put in the system remains in the system, it does not get dissipated. But here, whatever energy you put in the system, it either leaks out from infinity or it either goes into the horizon, and neither of which you can tap into. So that means black hole is not a conservative system to deal with. Black hole is actually a dissipative system. It leaks out energy at infinity, it leaks out energy at the horizon, none of which you have access to. I mean, you can jump into the horizon, but that's a different thing. I mean, you cannot extract it out. Fine. And that tells you that for dissipative system, it is sort of known that you should get an imaginary value for your normal mode frequencies, and that is why these are called quasi-normal mode. The quasi comes because the normal modes are imaginary. So that means the omega which is sitting here is not a real quantity. This omega sitting here is in general a complex number because of the fact that we have this particular feature which is associated with it. Okay, there is another interesting thing that happens on which Shubhadeep works, which is the fact that in quantum mechanics you have something called the spectral theorem, which tells you that if you have a if you have a energy eigenvalue and if you perturb the potential by a small amount, these eigenvalues are going to change only by a small amount. And the spectral theorem applies because your operators are Hermitian, which in turn is related to the fact that your boundary conditions are non-dissipative. In this particular case, your boundary conditions are dissipative, and that actually tells you that even if you add a small extra change, for example, this potential, if I add a small correction to it, the corresponding quasi-normal modes can actually be destabilized from their value by a large amount. So the spectral stability theorem that exists for quantum mechanical case no longer applies. For example, in quantum mechanics, you would do the perturbation theory analysis where you would say, to a harmonic oscillator potential, I would add a small anharmonic term and I want to find out how much the energy eigenvalues are modified. As you know, the energy eigenvalues are also modified by a small amount because your anharmonic term is small. For black hole, that is not the case. Your eigenvalues can change by a large amount even if you have added a very small perturbation. So this is something which makes black hole very different from other mechanical or quantum mechanical system that we study normally in our courses. But anyway, what does it mean mathematically? So mathematically, I have this kind of a time dependence which is e to the minus I omega t, and when r goes to infinity, as we discussed, all of this potential goes to 0, correct? So that means my differential equation becomes d2 psi dr star square plus omega square psi equal to 0. Right, everyone? So that means what is the most general solution for psi at infinity? Most general solution would be a e to the I omega r star plus b e to the minus I omega r star. Because at infinity there is no potential, so that means it's a free particle with an energy omega, and the solutions are e to the power plus minus I omega r star. Similarly, at the horizon, again as I have mentioned, all the potentials identically goes to 0 because of the 1 minus 2m by r in front. That means there also the solutions are plane waves, e to the power plus I omega x as well as e to the minus I omega x. So at the horizon, the solutions are c e to the I omega r star plus d e to the minus I omega r star. But the total psi would corresponds to the radial part times the time part, and time part we have taken to be e to the power minus I omega t. So that means I should have this guy multiplied with e to the minus I omega t, and this one multiplied also with e to the minus I omega t. Now after you have multiplied, you are asking for how do I identify that a wave is ingoing or a wave is outgoing. So when a wave propagates, what remains constant is its phase. So what is the phase in the first case? T minus R star, correct? Now if T minus R star has to remain constant, that means as T increases, R star should also increase. That means this is the mode which is outgoing and this is the mode which is ingoing, because its phase is T plus R star. So that means as T increases, R star has to decrease in order to keep T plus R star a constant. So this is my outgoing mode, this is my ingoing mode. Now what is the boundary condition? It should be purely outgoing as R star goes to infinity. That means that I must have B to be 0, because there cannot be any ingoing mode at infinity. Similarly, at the horizon, my perturbation should be purely ingoing. That means there cannot be a outgoing mode at the horizon. So I must have the solution at infinity to be e to the power plus I omega r star, and solution at at horizon, which is r star equal to minus infinity, to be e to the minus I omega r star. So this is the physics input that you give to the problem, and then you can solve for your quasi-normal modes. So to solve that, we will get back to this potential, and generally WKB methods are applicable when your energy is comparable to the maxima of the potential. So what you do, you assume that your omega is here, which is pretty close to the maxima of the potential, and you decompose the potential into 3 parts. This is region 3, this is region 2, and this is region 1. Yes. Ingoing modes are not 0, this is the outgoing mode, because it is minus T plus R star. So which is constant. So as T increases, R star also has to increase in order to make the difference constant. So R star increasing means you are going towards larger and larger R, which is the outgoing. Any other question? Where was I? Here. So the regions 1 and 3 are chosen in such a way that you have omega square, which is over there, is much larger than that of the potential, right? So that means in this region, if I come back to these equations and I will rewrite it as, let me remove all of this. So I will rewrite these equations as 1 by omega square d2 psi by dr star square plus 1 minus v by omega square psi equal to 0. So I will identify this as epsilon square and this as my q. So compare it with this equation which I have here. So that means epsilon much smaller than 1 translate to omega much larger than 1 or much larger than the maxima of the potential, right? Correct. So therefore this is the omega which I am choosing. So that omega is very large compared to the typical value of the potential in region 1 as well as in region 3. This is not true in region 2. That means the solution that I have written above using WKB method, I can use it to write down what is the solution for psi in region 1 as well as in region 3. Then I need to solve it separately in region 2 and I need to match. So you must have done this when you have doing the reflection and transmission of a particle which is passing through a rectangular barrier. What you did, there was a region where you solved it in terms of plane waves, there is another region where you solved it in terms of exponentials and you match them at the boundary. So here instead of having one boundary, you have two boundaries. So you have to match it here with 3, you have to match it here with 1. And the hope is when you do the matching, you will get a unique set of eigenvalues for omega, and this would be your QNMs. Right? Clear? Fine. So therefore, 3 o'clock. Okay. So therefore, following that analysis, which is over there, so I will move to this board now. So you can write down what is your psi I as well as psi 3, because they would be linear combinations of these quantities. Correct? Fine. And you see that I have written a square root of minus inside the square root. So if I keep it outside, I will get a factor of I over there, and that will exactly provide me this type of behavior. Why? Because let us look at what is the structure of Q. It is V over omega square, right? So when my potential is 0, right, then my Q is 1. Like, see, in these regions, region 1 and region 3, region 1 is when it goes towards infinity, region 2 is it is going towards the horizon. So in both these regions, my potential is much smaller compared to omega square. So my Q has a value which is 1, right? So that means here I will get a factor of I, right? So I will get e to the power I into x and e to the power minus I into x. The omega will be taken care of because this x and r star will have some extra factors which will take care of it. So you see that in general psi I will be exponential with a factor of a plus integral up to x root minus q of x dx. Then you will have b exponential minus up to x root minus qx dx, and similarly here you will have c with exponential with a plus sign, and then you have d with exponential with a minus sign, right? Yeah, because I have this as the general solution, there would be of course root minus q to the minus 1/4 overall, but modulo that I will have a term which is e to the power plus, and I will have another term which is e to the power minus. The same holds for region 3, because in both of these cases I can apply this WKB method because my omega square is much large compared to that of V, both in region 3 as well as in region 1, and hence these are the solutions that we can write. Please. Correct, correct.
So how do I say that omega square is less?
You cannot. So the point is, what you should do, which I have not done, is to rescale this quantity r star by a m, because you see r star has a dimension of length. So pardon me. Oh, he was asking about dimension. How can I take omega to be much larger and things like that? So I should not take omega to be much larger. What is generally done, you write down r star by m as your new coordinate, and then you see if you say it is r star over m, then it also becomes m 1 over. So it also becomes 1 over m square omega square. This m square omega square is a dimensionless quantity, and you can say m square omega square is much larger than 1. So I have just not done that because it effectively carries the meaning, but if you are keen on dimension, this is how you can make things dimensionless. And you see, when you do that, you also get a factor of m or omega over here, which originally was not present. Okay, so therefore you have these two solutions, but now you know what are the boundary conditions. Psi infinity has to be e to the power plus I omega r star, and psi horizon must be e to the power minus I omega r star. Psi infinity corresponds to the boundary condition over there, here at region 1, and psi horizon corresponds to boundary condition at region 3. That means not all A, B, C, D are non-zero. Actually, this quantity B has to be 0 because it gives you a minus sign. Similarly, here the quantity C has to be 0 because it gives you a plus sign. So that drastically reduces your solutions to just this and just this. So you have this the solution as region 1, this is the solution at region 3. Sure. So where was I? Yeah. So as I said, this is one solution where you can take both plus and minus, because it's a second order differential equation. We will have two solutions out of it. One would be exponential with a plus sign, one is exponential with a minus sign. The other one is also exponential with a plus sign and exponential with a minus sign. But this is generic. I have not applied any boundary condition. Now what boundary condition I am going to apply, I have already discussed over here. So region 1 corresponds to r star going to infinity. So there, as we know, that there is no term which is e to the power minus I into r star, because everything has to move out. There is nothing which is going in. So that means this term, which was exponential with a minus sign, should not be present. Similarly, the horizon, which corresponds to region 3, there we must have e to the power minus I omega, not plus, because everything must fall into the horizon. Nothing can come out of it. And as a consequence, exponential with plus sign must go to 0. So that fixes your solutions at psi 1 and psi 3. Next step is to solve it in region 2. And then you can match it with 1 and 3 and obtain your QNMs. Now the region 2, the way you solve it is again approximated, but the solution goes like this. So you have this equation which is 1 by omega square. Yes. Pardon me? Yeah. So you see what has happened here, that there would be omega coming from that epsilon, which I have missed. Exactly. Yes. So what I was trying to argue beforehand is that this x here is a dimensionless quantity, while r star here is dimensionless. So you can play around with x and r star with factors of omega. But as I said, I mean, if you take your epsilon here to be omega, or 1 by epsilon to be omega, then that automatically gives you exponential of omega psi naught, and then you will have a omega which is sitting here. I mean, you can interpret it in both ways. Okay. So what I was coming to is this equation. So I have omega square d2 psi by dr star square plus q to psi equal to 0. So this is the equation I have. Now region 2 concerns about a region near the maxima. So that means I can expand my q around that maxima. So if I expand that q around maxima, what happens? It is q at the maxima plus q prime at maxima plus q double prime at maxima, with of course x minus x maxima whole square and so on and so on. Now wherever v has a maxima, q will have a minima, maxima, that will come back to, but it will have an extremum. At least that much is sure. That means q prime at x maxima is going to be 0. So therefore we will approximate this as q at xm plus half q double prime at xm into x minus xm whole square. That is, we can approximate this q as that of a parabolic potential, because it ends up to quadratic order. I mean, of course, you can keep higher order terms, but then you cannot get an analytic solution. If you just restrict yourself up to the quadratic order, which should be more or less fine if you are just interested in a region around that maxima, then this equation is what you get. So this is the Schrodinger equation with a quadratic potential. Right? Yes. Sure. So q has a extrema where the potential has a maxima. So I am expanding about that maxima because the region 2 is around the maxima. So if I am expanding in Taylor series, first term is q at maxima, then I will have q prime at maxima, which is 0 because at extrema the first derivative vanishes. So I have contribution from second derivative and then the x minus xm whole square. So this is like a quadratic potential. And you can solve this equation. I mean, you can try it out at your home, and the solution is psi 2, which is some alpha d nu of, let me put it, t plus beta nu minus 1 of t, where these d's are known as the parabolic cylinder functions. Okay, so these are well known special functions, and you can just plug this in your Mathematica software, and you should be able to find out what is the corresponding result. And this nu which is appearing over here is the most important quantity, because mu plus half is minus I omega qm by 2 square root of is it 2 inside square root? Yes. So let me reiterate. I know what is the solution in region 1. I know what is the solution in region 2, and I can approximate the region 3. I can approximate the solution in region 2 by the parabolic cylinder functions, which has t which is related to x minus xm, and I have nu which is related to my omega by the following relation. Now everything is done. Now what you have to do? You have to take the limit of psi 2 towards region 1. You have to take limit of psi 2 towards region 3 and match with whatever psi 1 you have obtained and whatever psi 3 you have obtained. Yes. QM double prime, so that is what I tried to mention, that you see whenever, where was I? Yeah, whenever V has a maxima, Q will have a minima. So if V has positive, in the sense that V double prime is negative, which means it's a maxima, then Q double prime has to be positive. So if V has a maxima, which means V double prime is negative, then Q must have a minima, which means Q double prime has to be positive. That is why there is no I coming out of it. Right, and that would be very crucial in assessing the fact that black hole is stable. If it is other way around, as we will just see, that black hole will turn out to be unstable. So is this making sense? Okay. Now the limits of parabolic cylinder function, that is something I will not get into. I mean, there would be two terms, one will go as t to the power nu, and there would be another term which goes as t to the power minus nu minus 1, and you can match it with this exponential function. But I will just write you the final condition that you get. So you get two conditions. One is alpha equal to 0. The other condition is alpha minus beta, I think 2 pi to the power nu plus 1 divided by gamma 1 plus nu equal to 0. So you get these two boundary conditions. Okay, so this factor 2 pi to the nu plus 1, this can be slightly different, but that is not going to hit you because you can absorb it into beta in some way, which is anyway arbitrary constants. Yes. Qm is this Q at maxima. Is this one? Q double prime at maxima. Is this clear? Now what do you think is the solution? Alpha equal to 0, beta equal to 0, right? Then psi 2 itself is 0. The solution of this equation is because beta cannot be 0, whatever you do, then the only possibility is gamma of 1 plus nu should be divergent, and as you know, gamma function of negative integers diverge, so 1 plus nu should be negative of an integer, and then you have got your spectra because nu is related to omega, so you can immediately find out what is your omega. Correct? Right? Any question? That means I have nu plus half, which means what do I do? So I have half minus I omega qm by root 2 qm double prime equal to minus n, which implies that I omega qm n plus half. What happened? Then psi 2 is 0. It cannot be, right? I mean, how can you match? Then this 2 will also be 0. That's not physically relevant. Okay, again you refer to Sherlock Holmes, like, however impossible it is, if this seems to be a viable solution, then this is the solution. Right? Makes sense? Right? Any question? So that tells me that, where should I do it? Let me put it on top. Great. So that tells me omega into qm double prime is minus I into n plus half. Correct? Now what is qm? Qm also has omega square. Let me remind you. So that means qm will be 1 minus Vm by omega square. So I have to substitute it there. So this implies omega 1 minus V at maxima by omega square. Then you have square root of minus 2 V maxima see if you agree. I have done nothing. I have simply substituted for q, which is 1 minus V divided by omega square. Right, everybody? Should I proceed? Okay. This tells me that omega square minus Vm is equal to minus I n plus half into square root double prime, or omega square is equal to Vm minus I n plus half double prime. So you see that omega must have a real part as well as an imaginary part. And the imaginary part, in particular the sign of it, depends crucially on whether your V has a maxima or a minima. Because if V has a maxima, then Vm double prime is positive. You have a good I over there. If Vm double prime is a minima, then there would be another I coming from here, which will cancel that I over there. And then omega will be purely real. Right? Clear? But I want omega. I do not want omega square. So you should take a square root, and again there is an assumption in the sense that this is much larger than the second term over there. And as I said, this is an assumption, so you have to believe me. So omega n is going to be square root of Vm minus I n plus half square root of minus. Okay, if you just do a Taylor series expansion of the square root, you will get this. Fine? Clear? Yes. Yes, minus 2 V double prime at maximum. Fine? Clear? Now, suppose I compute e to the power minus I omega t. There would be one part which comes from the real part of omega, which will be oscillatory. But what about the other part? Can you tell me that if this function with this as omega decays with time or grows with time? It decays with time, right? And then you have black hole being stable. Because your parter being a black hole, these are its normal mode frequencies and they all decay with time. That means if I had waited for, I have given 1 hour 20 minutes lecture, by that time all the perturbation that I have started has decayed. right? Because it's, because of the sign over there. So this sign is extremely crucial. If it was plus, then I would not be standing here giving this talk. I would probably be at some other job because black holes would not exist, right? And maybe Professor Germany will have something to say about, cosmology, but black holes would not exist. So therefore, I would not be here to say anything if the sign was different. And if Vm is, minima, not a maxima, then there is no imaginary part, and in which case it will be purely oscillatory and it does not die out with time. That means even if I am seeing it today, the black hole will keep on ringing. It is not going to come down to a stable configuration, which is also some sort of an instability which is present. So that is why maxima of the photon sphere is extremely important. And why photon sphere? Because what does it depend on? None of this quantity depends on what happens at horizon. They only depend on what happens at the maxima, because this is related to the potential at the maxima. This is related to double derivative of the potential at the maxima, and that's all that matters. So the QNM that you see in LIGO, they are not a test of event horizon. In some way, in one way they are, because you see, in order to arrive at it, we have assumed this condition, that my wave function is purely ingoing at horizon. That is the only input that you have in this whole calculation about the horizon. Otherwise, horizon never enters. The QNM values that you see in the LIGO, they are coming from the photon sphere. They are not coming from the horizon. Okay, and in particular, you can relate it. Since I don't have time, I will not get into it. This quantity square root Vm, you can take it as an exercise, is related to the angular velocity at the photon sphere. So this object root Vm is written as L into ph, where omega ph is the angular velocity of the photon sphere. And this object over here, square root minus Vm double prime by 2 Vm, it also has a very nice interpretation. So as I said, if a particle is on the top of the photon sphere and if you perturb it slightly, it is going to fall down either way. Now the rate at which it falls down is what is characterized by something called the Lyapunov exponent. Because whenever you have some system which is unstable, there is a characteristic time scale over which this instability grows, and that characteristic time scale, it is what is called the Lyapunov exponent. You can compute the same Lyapunov exponent for the photon sphere, and you can show that that is same as this. So the imaginary part of the black hole QNM is related to the instability time scale of the photon sphere, which is the Lyapunov exponent. And the real part is related to the angular velocity of photons at the photon sphere. So there is nothing about the horizon. The only information that you have is about the photon sphere. Now in the last 5-10 minutes or so, I will discuss about alternatives of black holes and how you are going to detect them. So before that, which can I remove? I can actually remove all of it. So therefore, at the ring down, after your, okay, so this is going out of the card. So normally when you see any gravitational wave signal, it has, and my drawing is really bad, so please bear with me. Okay, you have a signal of this form, where this region is what you call as the in-spiral. Where these two black holes are moving around each other. This is the region which is called the merger, where these two black holes just merge. And finally, this region is what you call as the ring down region. So this is where you have a single black hole which is perturbed and it emits these QNMs and comes down to a stable configuration. If I zoom in here, what you will see is that there would be oscillations, and these oscillations are going to die away with time. So you have an exponential decay which is characterized by the imaginary part of the QNM, and you have an oscillatory feature which is characterized by the real part of the QNM. This is nothing like a damped harmonic oscillator, so to speak. So, but as I said, neither the decay time scale nor the oscillation time scale refer to the horizon. The only reference to the horizon comes from the fact that we have assumed my wave function to be purely ingoing at the horizon. Right? Yeah. But horizon is not a good thing. Why it is not a good thing? Because inside the horizon, what do you have? Singularity. Black hole has singularity at r equal to 0. Then you have the Hawking radiation, right? Black hole evaporates away and leaves nothing. So where does the information go, right? I mean, after this talk today night, for example, you find me to be very irritating and throw me into a black hole. Now, after that black hole evaporates, there is no reason. I mean, I am not there. I mean, my information is gone. My weight, for example, is lost from the universe forever. So therefore, and my color of specs, color of hair, everything is lost. So that is not a good thing. I mean, information is being lost. So therefore, people wanted to restore information, and that requires having no horizon. If there is no horizon, there is no information loss paradox. And then there are issues with what are called the Cauchy horizons, which happen inside the event horizon of rotating black holes, and then there are issues with the deterministic nature of GR and so on and so forth. So therefore, having no horizon is a very good thing. So I always make this quote at my talks. Maybe some of you have heard it. So if you have seen Superman versus Batman, Dawn of Justice, there is a saying that if you are all good, then you cannot be all powerful, and if you are all powerful, then you cannot be all good. So black hole is all powerful, right? Whatever you throw at it, it just absorbs it. It can do anything for you, but then it cannot be all good, and these are the reasons why it cannot be all good. But there are other objects which are not that powerful, means they are not black holes, but they are good. I mean, they do not have singularity, they do not have horizon, so there is no question of information loss paradox and so on and so forth. These objects are collectively called as ECOs or UCOs, whatever you prefer. ECO stands for exotic compact object, UCO stands for ultra compact object. Okay, so these objects which are compact than that of photon sphere, as I said yesterday, because you have black hole shadow, you have to be consistent with that observation, but it can be very close to that of the horizon. And you see, if it is even compact than photon sphere, then all the observations that LIGO has done will go unhindered, because LIGO is measuring the decay rate of a photon at the photon sphere, and the oscillation is related to the oscillation frequency of photon at the photon sphere. My object is compact than photon sphere, so I have a photon sphere. So all the results that LIGO has, I will also have for my object. The only issue with this object is how do you construct them and about their stability, in the sense like how compact can you make a star, for example. So that thing I will not get into details, maybe in the next class I will discuss them. For those objects, the way to compute the QNM is to change that boundary condition. Is to say that it is not purely ingoing, because it is not a black hole, but there can also be an outgoing part coming from it, which is referred to as imposing an reflective boundary condition at the horizon. And if you impose a reflective boundary condition, you can immediately see the consequences. You cannot set this term C to 0 and the rest of the calculation is going to be different. The consequence is, along with these modes which you have over there, you will have some other modes whose imaginary part are extremely small. And the upshot is, after some time, you will have additional repeated appearance of such oscillations. And these are known as, pronunciation wise, these are very difficult. Sorry, how do I pronounce this? Echoes. Okay, not ECO but ECHO, right? So these echoes are something which if you shout, it is going to come back to you at a repeated interval. Here also it is the same. So the way it changes is here. So here you actually put a reflecting surface. That's all that change. That means the wave that was going in now hits this and gets reflected back. So you see that reflected part again at infinity. Just think of it as a quantum mechanical problem. So you have, say, this kind of a potential barrier. You have a plane wave which is coming in from infinity. A part is going to get reflected, a part will get transmitted. The part which is transmitted will again get reflected from here, and that will also appear at infinity. After some time, how much time? The time that it takes for this object to travel this distance. Similarly, this time scale is same as the time that it takes for the perturbations to go from the photon sphere to the surface of these ultra compact objects and back. So therefore, if you ever see such signals in your gravitational wave spectrum, then you are sure that you are not looking at a black hole. Because black holes, by whatever means you try, can never give rise to such late time behavior which is present. So this is a fundamental test of black hole, not of GR. We are always in GR. Now what would be test of GR? Test of GR would be this QNM frequencies, if you remember, depends on the maxima of the photon sphere. Now the location of photon sphere and the potential both depends on what is your black hole. If you are not considering a Schwarzschild black hole, but some black hole in some other modified theories of gravity, then you will have a different maxima, different potential. So V at maxima, V double prime at maxima, they are all going to change. So that means the values of the QNM frequencies will be different compared to that of Schwarzschild. And that means you will have a different such curve, a different decay time, a different oscillation length scale. Then you can compare it with the data that LIGO has, and using that you can try to constrain these theories and say that whether we have some hint of theories beyond GR or not. And this is one of the key tests of GR, as well as I mentioned, one of the key tests of black hole. So whether we are really looking at black hole or not can be studied by understanding the QNM spectrum at late times. On the other hand, if you are looking at test of GR, you can just look at whatever we have from LIGO and test it against our favorite theory that we have. So both of them are going to give you a good constraint or on whatever theory you have. But if you see this, yes, I will come to you. Then you are sure that we do not have black holes, we have something else. It can be one of this exotic or ultra compact object. But if you see deviations here, then you are sure that it is not GR, it is probably some other theories of gravity. But the main problem here is to assess the mass of the black hole, because that enters here. So how do you know the mass of the final black hole? So for that, people actually uses a pretty convoluted thing. You know the initial masses of the black hole from the inspiral, then they run numerical relativity simulation to predict what is going to be the final mass, but numerical relativity assumes GR. So therefore, there is always an inherent bias in all the measurements that people report towards GR. So if you can do it independently, the final mass and spin of the black hole by some other method, then you of course can do much better analysis. And there are also other ways to get rid of this, which probably I will discuss at some stage. So I think with this I will stop and I will take any question. So next class will be on inspiral. So we have finished ring down. Now it is time to understand inspiral. The only two regimes which we can understand analytically. So yeah, I think I will stop. I will take your question.
So, I'm coming to the point that
Mm-hmm.
individual masses of compact objects when they are inspired. Can my QNM frequencies,
Hmm.
does they depend on, do they depend on the initial masses of?
No. No.
So now my next question is, then they do not, then they also do not depend on the formation channel, right? How the binaries
No,
are
they
formed?
only depend on your final black hole. There's
So
nothing
there
else.
so suppose there are two black holes. One is formed via stellar isolated evolution. Another one via dynamical interaction.
It doesn't care.
As long as the spin and
It does not care about the evolution channel. Yes.
So, as like many merging is happening, so I assume, let's say if I have a black hole which is merging head on, compared
Okay.
to a black hole which is merging like at some angle.
Mhm.
I just want to know, can there be a ring down which would be like kind of chaotic ring down? Or does it?
See, if they, I mean, merge head on, then there are some issues like the angular momentum and other things, because originally they would be doing this. But technically speaking, after they merge, they will just form a black hole, and that's all we are going to see. But what can happen is that there can be some kick, for example, which people say this natal kick of black hole. So that can distinguish, in the sense you can have the final black hole formed not in a static configuration, but maybe it's moving with some momenta. And as you know, as it is moving with some momenta, these frequencies will be redshifted. They will anyway be redshifted because they will be at a cosmological distance away. But in addition, there would be Doppler shift due to this, kick of the initial black hole, and that can shift your QNM frequencies. And it may appear to you as if it's a black hole with different masses and spin than it actually is. So these are additional complications that arises, which you need to understand somehow, like whether this black hole will have some velocity to move in, because all these calculations assume the black hole is not moving, it is sort of static in some sense. But if the black hole as a whole moves, the frequencies are going to change. Yes. Yes. Yeah, I need omega squared to be larger. I agree. The reason I chose it to be very close to Vmax is so that, where is it? Yeah, I can do it this way. Yeah.
And here the approximation was that when it took this value of omega,
Correct.
the real part is larger.
Yes. Yes. And that is generically true.
So it's true only for small values of n.
Small values of n means? No, in general, the real part is, yeah, you can say so, because if n is large, of course, this term can actually dominate. So, yeah, for small values of n, that is true. But what is very remarkable is that you can compute the same QNMs using fully numerical analysis, and they actually match to 1 part in 1000, right? So, even after all this approximation. So at the end of the day, if you just write down a research paper with this result, it will not be published. You have to do it numerically and verify that your result matches with it. So, and that's what, when you do, you realize that this is very accurate, and you can make it further accurate, because as I said, I have only kept up to up to order epsilon. You can add higher and higher terms. For example, people now use a 6th order WKB. This is a first order. You can keep up to e to the epsilon to the power 5 or 6 term, and then also you can play the same game and determine omega, which would be even more accurate. But of course, I cannot do it analytically, but numerical codes are available. And the most recent code and the most robust code are the spectral method, which I did not get time to discuss. And if you want, I think Shubhadeep will be happy to help you.
You said that black holes are dissipated systems.
Hmm.
The eigenvalues can vary
Can be complex.
Yeah.
Huh.
So already in my economic approximation, I have taken out that 2m by r cube term.
Correct.
So that can change my omega a lot.
No, not all perturbations are going to do that. If you add 2m by r cube, it will not change. But suppose to this, you add a small bump, right? Then you can show that it is going to change a lot. Or if you add, some sort of a oscillatory potential and things like that, there are some potentials for which people have shown that it can change a lot. Anything else? Yes. Mm-hmm. That would be tidal, right? I mean, that is the tidal effect effectively when you have two bodies. But here I am just talking about an isolated black hole. And if you have two body problem, nobody knows what is going to be the boundary condition, because you cannot solve two body problem. But what you can do, this tidal field, so you can only solve it in some intermediate region. So I will try to argue some of this in the next lecture. I will discuss two things if I get time. One is tidal heating, one is tidal love number. and there you will have these two bodies and things can be worked out. Anything else? Yes. Yes, yes. Yes. Yeah. Uh-huh. This is ingoing, this is outgoing. Okay, yeah. Mm-hmm. Correct, correct. The only physical mathematical reason that I can tell you is that this d of nu and d of minus nu minus 1 has different asymptotic expansion. So this d nu, when you expand asymptotically, it just involves positive powers of its argument. The other one, when you expand, it involves both positive as well as negative powers of its argument, and that is the reason why you get this. I don't think I have convinced you because it's not physical argument, but sure.
They are not the same functions, right? The alpha and beta coefficients of different.
They are different functions.
Q and
Yes, they have different. Just like for Bessel function, you would have one which is r to the power, like which vanishes at r equal to 0. The other is going to diverge at r equal to 0, kind of a thing. Infinity.
the symmetry
Yeah.
you are talking about is with respect to exponentials in 1 and 2.
Yeah, yeah.
That doesn't hold for the
Yeah, but that's just the boundary condition. But yeah, that's true. So D does not have that symmetry. T is x minus xm, I think square probably.
That is what is causing the confusion. The arguments are related to x minus, but the indices nu
Are
and
not.
minus nu minus 1 are different.
Yeah, so these are two independent parabolic cylinder function, and they have different behavior in the two regimes. So that is why you have this thing not being symmetric.